let's look at some attributes of polynomials. A lot of times we're very interested in the end behavior of a polynomial. And you can determine a lot from a polynomial based on its leading term. So you always look for the highest power of x, and then you look at that leading coefficient. Now, if this leading coefficient is positive and n is even, then the end behavior is up and up. It's going to go up and it's going to go up, because as it's very negative and then you raise it to a power, it's going to become very positive. And as it becomes very positive in x and you raise it to a positive power, it's going to become very positive as well. Now, if a is negative, this is just going to flip, because remember, if a is negative, that's a reflection across the x-axis. So it'll look something like this. It'll go down and down. When n is odd and a is positive, as x gets very large, it's going to shoot toward positive infinity. But as x gets very negative, it's going to go towards negative infinity. So it doesn't matter what it does in here. We're going to say this is down and then up. While if a is negative, that will reflect somehow across the x-axis. Now we're going to talk about the turning points, and these are the relative maxes or min. Polynomials go on forever. They have an infinite domain. And so the turning points are just where the slope changes from positive to negative or from negative to positive. So we can think about locally having a max or a min. So let's look at this equation right here. Y is 4x to the 4th plus 6x cubed minus x. Just looking at the leading coefficient, since the leading coefficient is positive and even, we know it's going to be up and up. So the end behavior we're going to say is up and then up. This is the left and this is the right. We can locate the turning points through about right here. We would need some sort of graphing tool that we don't have right now to find those exact values. But we know the function is decreasing from negative infinity to this point right here. And it's decreasing from this point to this point. And the function is increasing from this minimum to this maximum. And then it's increasing from this point on. Let's look at y as negative x squared plus 2x. Now we've graphed this one a couple of times. The leading coefficient is negative and the highest power is even. So the end behavior is down and down. Now we know this turning point right here is when x is equal to 2. All right, I can do this one if I factor in x out. So I'm going to have zeros at, oh no, this is x equal 1. Sorry about that. So I have zeros at 0 and at 2. I have an axis of symmetry at x equal to 1. So the function is increasing on negative infinity to 1, and it is decreasing on 1 to positive infinity. And don't worry about the endpoints. For the function y equals x cubed, the leading coefficient is positive, the highest power is odd, so this has end behavior of what? Down, and then up. Now this function has no turning points. It has an inflection point, which we've discussed before, but we're not going to get into it much more than that. And it is increasing from negative infinity to positive infinity. Now let's look at this function right here. I've got a leading coefficient that's negative. Highest power is odd. So the end behavior is up and then down. It has turning points, but again, I would need technology or more work to find out what they are. But I can look at the graph and I can see, and I'm just going to do it this way now. I'm going to divide these. The function is decreasing on this interval and on this interval, and increasing in that interval. So these are just a couple of ways you can analyze graphs of functions, of polynomials.